Hello and welcome to Linearization. Today's lesson is about how to work with curves by converting them to lines and make them easier to analyze, make them easier to understand. This is a common approach mostly physicists and mathematicians use. You should know how to change the variables. It's a very easy lesson. Let's concentrate on the screen and let me turn off the camera to learn it better.
By the way, if you are new to this channel, don't forget to subscribe and push the bell button to see more videos. Let's start. I do an experiment and I get a set of data like that. X is my independent variable and Y is my dependent variable. I'm gonna have a mathematical relation between Y and X. I'm gonna guess that relation. Okay, it could be AX plus B. It could be ax squared plus bx plus c. It could be also maybe a over x and so forth. Thousands of options. I can check one by one the values here and find the best relation. Another approach is using a graph. Here I may have a plot for y versus x. I have some points here, then I connect those points to find a curve or a line, and from the appearance of that curve or that line, I can guess the best relation. Something which is mostly used by physicists. Okay, let's do that. I plot it and I get a graph like that. From the appearance of the graph, it is not a line, so it could be a kind of parabolic relation. Something like y equals ax squared. How should I check that my hypothesis is true? How should I find the value or the best value for this A? Something which is in my mind at the beginning step is to check the values. I may substitute the value of X and the corresponding value for Y here and find the value for A. Let's name it A1. Then I put another X and the corresponding value for Y and find another A2, and then I continue for more and more values. Unfortunately, here I don't know how to find the best value for A, and I don't know how to check if that relation is true or no. Here, let's establish another column to check that hypothesis. Another column could be x squared. X squared is exactly the values of x, which have already raised to the power of 2. I name it z. Let's take the z as the new variable x squared. So I can rearrange the equation and write it like that. I rewrite it. Y equals az. Here I have packed x squared in the new variable z. Y versus z is very easy to check. Why? Because as you see, it's a line, and the slope of that line will be exactly something I'm looking for, A. But how should I know that my hypothesis has already been true? It's very easy. As you see here in the second graph, I have really plotted y versus x squared. If this is line, so I can get the best assumption here, I go back and then I check my hypothesis. Yes, my hypothesis has been true. If this is true, y versus z must be a line. If this is line, my hypothesis is true. It is confirmed. What should I do more? I can easily find the value of a, because a here in this line is the slope of that line. Suppose that this red line is best fit line. Okay, if this is best fit line, so the slope of that, it could be a value like 3 everything, is the best value for a. This approach is named linearization. I guess a relation which is mostly nonlinear, and then I convert it to a line by packing my variable, and then I check the properties of the line for finding the constants or the coefficients in the first assumption. This is linearization. Let's go for some examples. Okay, let's start by y equals 5x squared. This is parabola, you see, and it's not a line. I'm gonna linearize that. You know that the general format of a line is y equals mx plus b. The exponent of y and the exponent of x must be 1. Y is okay for me, but x unfortunately has the power of 2. What should I do? I should pack it. Let's pack x squared as a new variable like z, and then y versus z will be a line. Okay, so let's define y equals 5z, and don't forget x squared is exactly the z. Now y versus z is a line. Very easy. That's all. Don't forget, y versus z is really y versus x squared. Okay, this is a kind of linearization. Let's do another one, a trigonometric one. Y equals 4 sine of x. Sine is anyway a very complicated function. It's not a line. So what should I do to linearize that? I should pack sine of x. Here, let's define y equals 4z, and z is exactly sine of x. Z is not x, sine of x. So y versus z is a line. And don't forget, it's really y versus sine of x. So even we can linearize a trigonometric function. Suppose the sine of x is tangent of x. I will do the same thing. Suppose that this is cosine of x or cosine squared of x. Again, I will do the same thing. For example, suppose that y is equal to 4 cosine squared of x. Here I can pack cosine squared as a new variable like z. So again, y versus z will be a line. Look at this one. Y squared is equal to 6x. The form of the graph is something like this. How to linearize this? Let me remind you again, y is equal to mx plus b as the general format of a line. X is okay here. X has the exponent of 1. But I have big problem with y. Y is not in the form of y. It's y squared. What should I do here? Oh yes, let's pack y squared as a new variable like q. So here if I write q is equal to 6x, and if the q is exactly y squared, q versus x will be a line. Don't forget that q is exactly y squared, so I have already plotted y squared versus x. More than that, as the y squared is always a positive value, you should start the graph from the origin. Don't let the y to be negative because it cannot be negative. Okay, let's go for the other one. This example is something from the physics. If I have a pendulum with the length of L, and here is the bob, and if I let the pendulum to swing with a small amplitude, the period, the time I need for a complete oscillation will be 2 pi square root of L over g. G is the gravitational acceleration, which is almost 9.8, and L is the length of that pendulum. L is my independent variable. Anyway, I can change the L. L could be longer, could be shorter. So T is a constant multiplied by square root of L. And this constant will include 2 pi and square root of g in the denominator. Anyway, I think that t versus L will not be a line as it has a square root here, but the form of the function must be something like that. Okay, so the form of t versus L is this. What should I do to linearize that? Anyway, let's take all the constants here in the bracket and then let the square root of L to be out of them. Here I see that if I make a new packing for square root of L, let's name it z. Here t versus square root of L, as square root of L is my new variable z, will be a line. This is one approach for linearization. Also, you can do something more. Let's raise both sides to the power of 2. Here I will have t squared is equal to those constants to the power of 2, which is not that important for me, and square root of L will be L here. Now I don't have any problem with that L. L is okay, but t squared must be packed again. let's name it a new variable like q. So here if I draw the q versus L, which is really t squared versus L, it will be also a line. Another example could be P is equal to nRT over V. Suppose that I put an ideal gas in a container with the pressure of P with the volume of V and the temperature of T. Temperature is Kelvin temperature here. R is ideal gas constant and N is the number of moles. If the gas undergoes isothermal process, during that process, temperature is constant. So I can take all the upstairs to be a constant. So practically P is proportional to inverse of the volume. By this condition, I can have P versus V as an inverse function like this. It is not a line, and I'm gonna take it as a line, convert it to a line, linearize that. What should I do? I should define a new packing for that. 1 over V could be hidden, and we can name it as Z, the new variable. So P versus Z will be a line. That's all. Don't forget that. Indeed, P versus Z is P versus 1 over V. This is also a kind of linearization. This example is about radioactivity. Suppose that in a box I have certain amount of radioactive material and the total number of atoms will be N0. Okay? N0 is the initial number of radioactive atoms. After T seconds, they will disintegrate and then I will have the total number of remaining atoms to be N as the final value. Okay, N0 initial number of atoms, N final number of atoms after T seconds. Lambda is decay constant, is a constant, it's a property of radioactive material, and E is the Euler's number. What should I do here? Anyway, this relation could be an exponential relation. If you put T is equal to 0, N will be N0 e to the power of 0, which is 1. So it starts from N0, and the form of the function could be something like this, exponential. Okay, this is not linear. What should I do to linearize that? I should first get rid of the Euler number. The best strategy is taking the natural logarithm from both sides, ln. If I take that, here I will have ln of n on the right side, ln of n0 plus ln of e to the power of negative lambda t. We know that natural logarithm of e to the power of x will be x. So easily we will get ln of n to be equal to ln of n0 minus lambda t. Okay, this is good. I think we are getting closer to the linearization. Here I can take ln of n as the q, natural logarithm of n0 to be the constant, which is the y-intercept of the line. Lambda plays the role of the slope, and t is my variable. So if I plot natural logarithm of n versus t, it will start from a, which is natural logarithm of n0, and it's a descending line like that, and the slope of that line will be b. Example: an experiment was carried out to measure the extension x of a thread of a spider's web when a load F is applied to it. On vertical axis, I see the force multiplied by 10 to negative 2. So everything I read on vertical axis will be, for example, this one, 7 times 10 to negative 2 in newtons. And on horizontal axis, everything I read is the extension of that web. For example, 5 will be 5 times 10 to negative 2 in meters. Okay. Part A. Copy the graph and draw the best fit line for the data points. The best fit line here could be a curve passing through all data points as possible. Something like that. Part B. The relationship between f and x is of the form of f equals k x to the power of n, exponential form. State and explain the graph you would plot in order to determine the value n. You know that linearization here is the best strategy. What should I do for linearization? I can take, for example, natural logarithm. If I do that, I will get rid of the exponential case. So ln of f will be ln of k plus ln of x to the power of n. N can be taken out of the logarithm to be here as a coefficient, so here I can define my new variable. Let's take ln of f to be the vertical axis y and ln of x to be the horizontal axis as a capital X, something like that. So it's good. If I plot capital X versus capital Y, versus capital X, it will be a line. This line will start from ln of k here. Let's take it ln of k, and then it will be ascending line with a slope of n. Good. That's all. Look at this again. I can show you again. Ln of f will be ln of k plus n natural logarithm of x. Okay? Here I make an analogy. Natural logarithm of f could be my new variable, capital Y. B is the constant, vertical intercept, and n is the slope of that line. Ln of x is my new variable, capital X. So here I will plot natural logarithm of f versus natural logarithm of x. It will start from ln of k, and it's an ascending line. The slope also will be n. If I establish a right triangle here, I can find the slope of this line, which is exactly the value of n. This is the strategy I may use, linearization. Okay. Part C. When a load is applied to a material, it is said to be under stress. The magnitude of P, this is the stress, of the stress is given by P is equal to F over A, where A is the cross-sectional area of the sample of the material. Suppose that this is, for example, a cable, and A is the cross-sectional area of that cable here, okay? If I make a tension like F, the stress is defined as, P is defined as F over A, force over area, in Newton per meter squared. Stress is very similar to the pressure, but the pressure has different property. As when you put something under pressure, the force must be inwards to compress the material, but when you put an extension on that, it will be under stress. So stress and the pressure are very similar in the form of definition, mathematical definition, force over area, but stress is something to be an extension, an extensive form, but pressure is something as compress the object. Exactly the same, but inwards. Okay. For the spider's web, of course, it's stress, not the pressure. Use the graph and the data below to deduce that the thread used in the experiment has greater breaking stress than steel. Here the thread breaks at this point, okay? This is the maximum stress it can tolerate, okay? Breaking stress of steel is given here, and radius of the spider's web thread is this. Radius is exactly here. Let me show you something. Suppose that here I have a cross-sectional area like A, and the radius of this circle will be R. Okay, this is exactly the radius of that. Okay, as I suppose that the thread of that web will be a kind of cylindrical shape. Okay, let's do it. Based on the definition, the stress will be force over area, and as you know, the area of a circle will be, if the radius is r, will be pi r squared. So I've substituted the area for pi r squared. Then I put the values. Here, estimately the thread breaks at this point, so it may be about 8.5, 10 to negative 2 newtons. So I substitute the value here, and pi 3.14 multiplied by the radius. Okay, radius is given here. I've just directly substituted the value. So the stress is 1.3 10 to 9 Newton meter. It's interesting. As you see, the stress you need to break the thread, the web, the spider's web, is 1.3 10 to 9, but for the steel, it's 1 10 to 9. It's more resistive than steel. It's interesting. Part D. The uncertainty in the measurement of the radius of the thread is this. The uncertainty is given, okay? Determine the percentage uncertainty in the value of the area of the thread. Okay. Let's go back to the definition of area. For a circle with the radius of r, area is defined as pi r squared. I'm looking for the percentage uncertainty of area. So I'm looking for delta A over A. From the previous videos, I have already told you how to find that percentage uncertainty. I should write delta A over A to be 2 delta R over R. And you should forget about the pi as it is a constant. So the exponent goes as a coefficient here, like 2 delta R over R. Let's substitute the values. Here, delta A over A, the percentage uncertainty will be 2 times. Delta R is exactly the uncertainty of the radius given here. And the downstairs will be substituted for 4.5 10 to negative 6 according to the given value for the radius. The answer may be 28%. This is the percentage uncertainty for the area. Okay, thank you for watching this video. I hope you liked it. If you liked it, give a like and don't forget to subscribe if you are new to this channel. See you in the next video.